The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So last time we talked about how to describe, say, if the boundary CFT is at a finite temperature, what would be its gravity description? Okay. So what we described was a thermal theory, say a thermal CFT on the flat space. Okay. We showed that this is related to a black hole with planet with a planar horizon. Okay. The key is that the horizon should have the same topology as the boundary space, So in terms of the picture, this is your boundary. So this is z equal to 0. And then the horizon somewhere, say, at some value of z0. So horizon at some value of z0. And the horizon have the same topology as the boundary space. Okay? And then you can do it thermodynamics, etc. So any questions about that? Good. So one can also, so previously we also briefly discussed that ADS-CFT also allow you to put the field theory on the sphere. So if you put the field theory on the sphere, then that would be dual to the global ADS. Okay? Now you can ask the same question. What happens if we put the boundary theory on the sphere and then put it at the finite temperature? Okay? So let us consider put CFT on the sphere at the finite temperature. So the story here is much richer for a very simple reason. So if you have a CFT just on the RD minus 1, okay? So this RD minus 1 does not, this Euclidean flat space does not have a scale. And the CFT does not have a scale. Okay? So if you put it at the finite temperature, then the temperature is the only scale. And essentially provide a unit of the scale. Okay? So the temperature is the only scale. So essentially providing energy unit. Okay? So this means that for CFT on the finite temperature, CFT on the flat space, then physics at all temperature are the same. Okay? So they are just related by by a scaling of units. Okay. So in some sense, if you can see the in some sense the physics very simple. Whether you have like 0.0001 degree or you have 10,000 degree, doesn't matter, and it's only the relative scale matters. So the physics at all temperatures are the same. There's no difference between low temperature and high temperature, and the temperature just provides you the units. Okay. But if you put the CFT, but for CFT on the sphere, now the story is different. Okay. So for CFT on the sphere, because the sphere has a side itself. Okay. So let's take the sphere have the sides r. Again, when you put the CFT on the sphere, the size of the sphere does not matter, because again the size of the sphere essentially provide the units, okay, because the series scale invariant. So let's just put the sides to be r. So let's take sides to be r, and r will be can be chosen to be the same as the curvature radius in the block, just to make formulas simple, and you can choose it to be any radius. Okay. And now, since the sphere already have a sides, and now you put it at the finite temperature. Now you have a dimensionless number, okay? Then at the finite temperature, then the physics is controlled by a dimensionless number, r times t, okay? So now, the temperature makes a difference. Now different temperature are different, because now you have a relative scale, and if RT is small, then essentially you are at the low temperature, and when RT is big, then you are at high temperature. Now there's a dimensionless number to characterize whether you are in the low temperature or in the high temperature. Okay, so the physics essentially become much richer because of and then you have a whole parameter the physics can depend on. Okay? And so indeed, the story becomes rather intricate when we consider the finite temperature theory on the sphere. So now let me just mention some important features. Okay, so I will walk you, say, not too slowly, but also not too quickly, about the physics on the sphere. Yeah, we cannot afford to do it very slowly at this time. Yeah, but if I do it too quickly, of course, you won't learn anything. Okay, so let me just point out some important features. So first, when we talk about the story last week, when we talk about the finite temperature on the flat space, we said, or probably there are two possible descriptions for finite temperature theory from the Bach point of view. So one is that you can have a thermal gas, okay? You can have a thermal gas in ADS. But then we argued that for theory on the sphere, that's not allowed because you encounter singularity because the metric becomes singular. Okay? And one big difference for the theory on the sphere is that actually now this is allowed. Okay? So the thermal gas in ADS now is allowed. Okay? So now let's go through the argument. So now first let me just write down the global ADS metric. Okay. Of course, you can write it in many different coordinates. So the most convenient coordinate to write global ADS for our purpose is the following. So this is just a pure ADS. and r goes to 0 to infinity. So this is like somewhat analog of, say, spherical coordinate in flat space. Okay. But the difference is, of course, now you have this non-trivial curved non-trivial factors which tell you are in the curved space, in the curved space time. Okay. So now, to go to the thermal ADS, we do the trick you normally do for thermal field theory. Is that you go to Euclidean space, okay, and then you put the Euclidean time to be periodic in the inverse temperature. Okay, in the inverse temperature. So actually, let me write down here the analogous metric from the sphere. So this is the situation we considered before for the theory on the flat space, on the plane, and that would be the metric to be on the sphere. So we talked about last time. If you make tau to be periodic, then when Sz goes to infinity, then this circle shrinks to 0 sides because the prefactor goes to 0. Okay, so the tau circle have a size beta, but the proper length is controlled by the prefactor, and because then when z goes to infinity, then the proper length of the circle will go to 0. So whenever you have a circle which shrinks to 0, then you have a singular behavior, etc. And then the matrix singular. So you can have various singular behavior, and so that's why this is not allowed. Okay. But now in this case, when you do such analytic cantillation, this becomes well defined. Okay. Because the proper size of the tau circle. So now you local proper length, local proper size of the tau circle is just given by this prefactor, 1 plus r squared divided by beta 1 squared by r squared beta. Okay? And since r equal, greater than equal to 0, so this is greater equal to beta. Okay? So actually, this is bounded from below. So this is bounded from below. So this circle level becomes too small. Okay? Essentially, the minimal size of the circle is the same as the beta itself. Okay? So this Euclidean metric is perfectly well defined. Okay? So Euclidean metric well defined. So in contrast here, the Euclidean metric is singular. As z goes to infinity. Okay. So in the if you put the theory on the flat space, then that's not allowed, but in this case allowed. Okay. So for the theory on the sphere, but still there's an analog of a black hole solution. You can also find a black hole. Again, you just write down the standard spherical symmetric ansatz for black hole metric, and then you solve Einstein equation. Then you find, so let me just write down the answer. So you find that this space also allows a black hole solution. Can be written as follows. Okay. So now f, just slightly generalization of this factor. So the mu is a parameter related to black hole mass, for example. Okay. And the horizon is at r equal to r0, and r0 satisfies that this factor goes to 0. Okay. So you can also find out what is the temperature associated with this black hole. So here the beta can be anything, okay? Beta can be anything. There's no constraint on the beta. Okay? So here you can just find you in the standard technique to find what is the Hawking temperature for this black hole. Let me just write down the answer. So this is just 4 pi divided by f prime evaluated at the horizon, standard formula, and you just find the 0 of this guy, and then you just take the derivative. So you can find so you find the beta can be written in terms of r0 as follows. So this is just a simple algebra. Okay? So you find that if you take the derivative and then re-express the derivative in terms of r0, then you find the Hawking temperature of the following form. Yeah, I'm not doing this calculation here. You can easily check yourself. Okay? Good. Any questions so far? So now it seems like we have a problem. Because we have a black hole, we also have a standard thermal ADS. Then which one is the right description for the field theory at the finite temperature? Okay. Seems like we have a choice. But now, if you look at this function, the story is even more tricky than that. So let's plot this function, just the rough behavior of this function. So this is the temperature. So this is the inverse temperature, and this is the size of the horizon. Okay, and the size of the horizon essentially determines your entropy. Okay, so it's really a physical thing here, because the area of the horizon is the entropy. The area of the horizon is the entropy. So this R0 can be considered as something stands for entropy. Okay. So now let's just to get intuition. This is a complicated function. Let's get intuition that how this beta depends on this R0, the horizon size. Suppose horizon size is very small, R0 goes to 0. Then downstairs is finite, upstairs goes to 0. So you just goes to 0. Okay. And when R0 is very large, so the downstairs proportional to R0 square, but upstairs only proportional to R0. So when R0 is very large, it should go to 0 as the R0. Okay? And this is a smooth function. So there must be a maximum somewhere. Okay? And of course, you can easily find the maximum just to take the derivative of that function. Anyway, so that's how the beta will depend on R. But now this plot is highly peculiar. Why? Can you tell me why?
Bound on temperature?
There's a maximum on beta, which means
Minimum
That's right. So there's a beta max. So that means, so this is there's a beta max, which tells you there's a T minimum. There's a minimum temperature. That means that black hole solution only exists above a certain minimal temperature. Okay, and you can easily find out what is that minimal temperature just by taking the derivative of this function, and it will require it to be 0. Okay. And what's other? Is there any other thing peculiar regarding this plot?
When R is 0. When R is 0, that means no black hole.
When R0 is 0, the black hole becomes smaller and smaller. It means there's no black hole.
No, but by the temperature is infinity. By the temperature, there is infinity.
Yeah.
That's weird.
No, that's not weird.
Not weird.
No, that's the standard flat space black hole behaves that way. Just look at the Schwarzschild black hole in flat space. When the horizon size becomes smaller and smaller, the temperature becomes higher and higher. Yeah, so that's the that's the standard feature of flat space black hole. Yes.
Okay, so it must be the other way. I mean, if you have a huge black hole, then why is it that this beta goes down? That seems bizarre. I mean, maybe that's all. That can't also be standard, right?
Both of things you said are correct and are important, but there's something more elementary you're not pointing out. You're pointing out the higher order important things. But there's a one lower order important thing which is not yet pointed out.
There are two solutions of the same temperature.
Exactly. In terms of the temperature, this is multi-valued. So if you look at the given temperature, there are actually two solutions. Okay? So for any given temperature, there are two solutions. Say T greater than T min. So this is for the beta smaller than beta max, means the T greater than P min. There are two solutions. Okay? And we have to label them. So let's very imaginatively call this one the big black hole, and this one the small black hole, because this one have a larger size, this one have a smaller size. So this corresponding to the R0 of these two. Okay. So you have two black hole solutions. One have a larger radius than the other one. So we have big black hole and a small black hole. And now this is an important thing you mentioned, that for the small black hole, the temperature, when you increase the size, decrease the size. When you decrease the size, the beta decrease. That means the temperature increase. Okay. So, and this, as I said, is like entropy. So if you lower the entropy, somehow your temperature increases. Okay. So when you increase the temperature, you actually lower the entropy for the small black hole. The small black hole, you go like this. Go like this. When you reduce the size, you reduce the beta, means you increase the temperature. Okay. But this is actually the standard Schwarzschild black hole behavior in flat space. And this just tells you this have active specific heat. So this is a situation we understand. This is a situation we encounter for the flat space Schwarzschild black hole. And it makes sense why it's happening here. Because here, roughly, is order R. So because the R is the scale here. So the maximum location of the maximum is controlled by the R. So this region corresponding to the size of the black hole to be much, much smaller than ADS curvature radius. So when something is much smaller than the ADS curvature radius, what should you see?
Flat space?
Yeah, flat space. Yeah, it's just like we, even though we live in the curved universe, but we actually see flat space because, of course, our scale is much smaller than the curvature radius of the universe. And a similar thing here, if the black hole have a size much smaller than the curvature radius of ADS, then essentially behave like flat space black hole. And so that's exactly what you see for the flat space black hole. And indeed, the more interesting is this big black hole. The interesting is the big black hole. And the big black hole, when R0 increases, the temperature increases. Okay? So this is the right way. So this is indeed the right way, the standard. Yeah, just positive specific heat. You can check it have positive specific heat. So this is indeed what you expect from a thermal system. Okay, so this is indeed what you expect from a thermal system. So now we are encountering even weirder situation. We not only have thermal ADS, we not only have black hole, we actually have two black holes. Okay? So what is the story? So what actually describes the field theory at finite temperature? Okay? So what does this really mean? Number two is a black hole solution. So now let's look at the number 3. Okay? So now let's look at what are the interpretation of those solutions. Okay? So first you can just guess. So what do you think these 3 solutions should mean? If you believe this duality has to be true. Yeah, so the game we play here is that you believe the duality is always true. And then whenever you see some phenomenon on the gravity side, you say, let's try to interpret, I try to understand on the field theory side. And it makes sense. And then we just carry out the guess and check it, etc. Okay? So what would be the 3 solution means? 3 gravity solutions. Or in principle, for example, for temperature at here, we can have 3 solutions all have the same temperature. Okay? What would this mean? So the simplest guess is that it tells you that for CFT on the ST-1 at this temperature, there are 3 possible phases. Okay? There's 3 possible phases. It's just like water, ice, or vapor. Okay? There's 3 possible phases. And then to decide which is the right solution, then now the interpretation is clear. Then we should just find so to decide what is the right solution, then we should find what? That's right. We should find the phase, find the one with the lowest free energy. Okay? And to decide which is the right one, we just need to find the one with the lowest free energy. Okay? So now recall that the partition function in the field theory side should always be identified with the partition function on the gravity side. Okay? And this side, the partition function by definition is minus beta, the free energy. Okay? Seems like going more and more That's weird. So, but on the gravity side, we evaluate this by saddle point approximation. We integrate over all possible fields on the gravity side, weighted by the Euclidean action. Okay, and the leading order in the saddle point approximation, you just evaluate it. You just evaluate it on the classical solutions. Okay. So this led us to the so now you can just you just equate them. You just lead to the free energy must be equal to SE to the phi c. Okay. So this is just the same principle we discussed before. Now we just apply it to the. So now if we believe the duality and we believe thermodynamics, then we should just find the solution with the largest SE. Okay? So we should calculate the Euclidean action for all three solutions. And then we find the corresponding free energy for each of them. And the one with the largest SE will correspond to the one with the lowest free energy. Then that will be the stable solution. And the other phases presumably will be unstable or metastable. Okay? Just like in the standard story. So this conclusion was drawn from the thermodynamic itself. But it would be nice we can actually draw this conclusion without using thermodynamics. Okay? So we say if we equip with, so this conclusion was drawn to identify this with a free energy, and then we say according to the thermodynamics, and then we should choose the one with the lowest free energy. But it would be better if you can actually derive this thing from the gravity side. And you can. And for a very simple reason. So this also follows from the rules of the saddle point approximation, from the standard rules of saddle point approximation. As follows. Oh, I forgot to write on this board. Okay. So now you can. So you actually don't need to use the free. So when you do the side. So when you evaluate this path integral. So when you evaluate an integral using the saddle point approximation. So normally you are instructed to add the contribution of all saddle points. So the fact that you have three different solutions, it tells you have three separate saddle points. Okay? And then you are then just from the standard rule of the saddle point approximation, you just need to add all of them together. So you add the exponential SE evaluated at thermal ADS, and the exponential SE evaluated at the big black hole, and then you add the SE at the small black hole, etc. Okay, you add all of them together. And now each action is in the exponential. And as I said, they are weighted. All these actions are weighted by n squared, okay? Because the action is always proportional to 1 over g Newton, and 1 over g Newton is proportional to n squared. So there's a big parameter in the exponential. So the saddle with largest SE dominates. in the Lagrange limit. Okay? Yeah, you just add 3 exponentials. Which one is the biggest will dominate. Because naively, each one of them is proportional to n squared, and n goes to infinity. Okay? And then in the n goes to infinity limit, then even you is greater than the other guy by a tiny bit in the prefactor of n squared, they will be completely dominant. Okay? So we see that the thermodynamics tells us we should find the smallest free energy. And that statement can be essentially derived if I don't know that statement. I can actually derive that rule, say finding the smallest free energy, just by using the standard saddle point approximation from the gravity side. Okay? From the saddle point. Yeah, so this is a nice consistency check. So this is a nice consistent check that the duality which we believe to be true should be true. Okay? Yes?
Okay, so the one thing I don't totally understand is that, so say that you give me this Euclidean integral over metrics on the gravity side. So the idea that there's really only 3 contributions, right? Because we found 3 solutions with a particular temperature. How do we know that there aren't any other solution? Like, how do we know there aren't any other terms that we're not accounting for?
Oh yeah, there are 3. So this is the rule of the saddle point approximation, right? You find the saddle point. Say you find the solution of the you find the solution of the equation of motion with the right boundary conditions, and these are the only ones.
Okay, sure.
Yeah, and then of course each of them include the fluctuations, and for each of them including the fluctuations, and yeah, and of course because yeah, this is just the standard saddle point approximation. Sure. Yeah. Any other questions? So now the task just boils down to yeah. Let me just emphasize here. So now the task just boils down to find what is the lowest free energy. Okay. So now it's 3, now it's 4. So now let's try to decide which one is more stable. So first, let me just emphasize that SE is proportional to the 1 Newton, 1 over g Newton, and then it's always proportional to n squared. Okay? Because 1 over g Newton is proportional to n squared if you translate from the field theory language. And now if you evaluate the free energy for them, for this, yeah, let me call this, so thermal gas in ADS, I always just call it TADS, okay? Thermal ADS. I think, yeah, I just, shorthand just thermal ADS. So for the thermal ADS, this is actually 0. This is actually 0. So thermal ADS, the free energy, yeah, I should say this way, SE is actually 0 times n squared. And then you can have fluctuations, then can contribute to the order n to the d power 0 contribution. So the 0 and this is 0 is simple. It's because when we go from the pure ADS into the thermal ADS, essentially we just change the global structure. Okay? We just make the Euclidean circle. So for the pure ADS, when you go to Euclidean space, the tau have infinite sides. And then when you go to the thermal ADS, we just make the tau to be a compact circle. So you have not changed the solution is identical. The solution is identical to the pure ADS. Just the global structure is different in terms of the periodicity of the Euclidean time circle. So now if you evaluate the classical action, So if your reference point is the pure ADS, the classical action is 0. And then for the thermal ADS will be 0. Okay? Will be the same. Because it will be the same. The classical action will be the same as pure ADS. Okay? So to leading order is n squared, but then you can have fluctuations which contribute. And the fluctuations is the so the fluctuations can be interpreted as the graviton thermal contribution from the thermal graviton gas. Okay, and so say in the thermal ADS you can essentially have a thermal gas of graviton, and their free energy is independent of n, because they are the fluctuations. Okay, and just as usual, whenever consider the fluctuations, they're independent of the coupling constant. Is this clear?
Why the first term is 0?
Hmm?
Why the first term is 0?
The first term is 0 because this have the same classical solution as the pure ADS.
But pure ADS then has a non-zero Ricci tensor.
Yeah. Yeah, that's a very good question.
And the action is Ricci.
Yeah. I will. Yeah. Wait a few minutes. I will talk about this more precisely. It's a good question.
Okay.
Yeah. Okay. Let me just tell you the answer first, and then I will say a few things. Okay. Any other questions? Okay. And then if you calculate the Euclidean action for the big black hole and the small black hole, you find that they're always greater than that. It's always larger than the action for the small black hole. Okay? And this is some number, non-zero number times order n squared. Okay? So this is always the case. So I will outline a way for you to calculate in a few minutes, but I will not do this explicit calculation here because it takes some time. So there's a simple way, physical way to understand this, to understand why this is true, because this is a free energy. So this tells us that the free energy of the big black hole is always it's always smaller than the free energy of the small black hole. Okay. This is not the precise way to understand it, but it's a heuristic way. It said if you look at these two solutions, so these two solutions have the same temperature, but the big black hole have a larger size. When you have a larger size, and the entropy is proportional to the area of the horizon, and the entropy is much higher. So the big black hole have much higher entropy than the small black hole. And so intuitively, you would expect that this should have a smaller free energy. But of course, you have to do a precise calculation to really check it, because their energy is not the same. The energy is also not the same. Yeah, but this is a heuristic way to understand it. Anyway, so you find that the free energy, so you find the Euclidean action of the big black hole is always greater than the small black hole. And that is good. That is good, because that tells you the small black hole is never dominate. Because you always find something bigger than that. And the small black hole have a lactive specific heat. That's not something you want, because our field theories definitely have positive specific heat. Okay, our field theory definitely have positive specific heat. So that tells you that this is never never be a dominant phase. Okay. So now if you calculate the number, so now if you look at the number explicitly, so what you find actually so you also, let me just first tell you the result, okay? You find there exists a temperature Tc, which is greater than the minimal temperature. Okay. Then you find that when you're smaller than the minimal temperature, yeah, right. Okay. So when your T is smaller than the minimal temperature, oh, no. When T is smaller than Tc. So you find that there exists a Tc which is greater than the minimal temperature. So, yeah, let me just say this. So when T is smaller than T minimum, of course, there's only thermal ADS exists. Okay? And of course, that would be the only phase which can describe the field theory result. But now there exists a lot of temperature. Then within the T smaller than greater than T minimum and smaller than Tc, then you find that the SE, big black hole, is smaller than 0. And the thermal ADS essentially by definition to be 0. So that means that the thermal ADS will have a lower free energy. Okay? So in this range, the thermal ADS will dominate. Okay? And when T is greater than Tc, then you find that the big black hole now have a positive action, and then it will dominate. Okay? So if I draw this, and then there's a Tc, then there's a T minimum. So this is the temperature axis. So here, of course, you only have a thermal ADS. But within this range, the thermal ADS dominates over big black hole and the small black hole. And when you're above then the big black hole dominates. So you actually have a transition at Tc. So below here, you just thermal ADS. Then you have a transition from thermal ADS to big black hole at Tc. Okay? So a quick side remark: how would you find this? How would you find this result? So this would be the result if you calculate those. Say, so you just calculate the Euclidean action. You compare them. That's what you find. Okay. So any questions about that? Yes?
Can you ever get the small black hole phase at all, somehow, artificially?
Yeah, you can always get artificially. Yeah, artificially you can always. Yeah. Let me not go into that. So now let me just say a few remarks, say in finding SE. Okay. So when you find the Euclidean action, you find it's always divergent. It's the same thing as what we encountered before. If you calculate the whole action, you have to integrate over essentially the volume of the ADS. But the volume of ADS goes to infinity at near the boundary, so essentially always get infinity. So in order to get the finite answer, you need the realization. Okay. So when you do the normalization, you essentially you put the cutoff, then you subtract covariant the local counter terms. Okay, you put the cutoff. You put the cutoff. And then you subtract covariant counter terms at the cutoff, and then you get the finite answer, then you take the cutoff to the boundary. Okay? So I will not go through this procedure. But it's something you can do. Okay? Something you can do. But there's an alternative shortcut to not go through this. Is that all you can just subtract, just calculate the Euclidean action, put the cutoff, then subtract the value of pure ADS. So if you calculate the pure ADS, you find the answer is also divergent. Okay, you find the answer is also divergent, and you just subtract it, and then when you do the subtraction, you find the difference is finite. Okay, and then you find the difference is finite. And this is a slightly simpler way to do than that. But we will also not do this, because this still you have to calculate Euclidean action, etc. So the simplest shortcut is to assume thermodynamics, okay, as what we did last time, because you can find the entropy density very easily. So entropy density, did I erase my? So entropy density is just essentially the area of the horizon. So the entropy right now is actually the total entropy, not entropy density, because now we are on the sphere. So the entropy would be the size of the sphere would be R0 to the power d minus 1 times omega d minus 1. Omega is the volume of a unit sphere, okay? And then divided by 4gn. So this is the entropy of the system. Okay, and you can express it this in terms of the temperature, because R0 is a function of temperature. So R0 is a function of temperature. If you invert this, you can imagine R0 is a function of temperature. Okay, so you have essentially have entropy as a function of temperature. And
D minus 1 offset.
Omega d minus 1 is the volume of the unit sphere. Volume of unit sphere. Okay. So you know the entropy, you can just use the formula S equal to minus F minus T divided by T to, so you can also write it as minus F R0, partial T, etc. And then you can integrate this equation to find F as a function of R0. Okay? Because we know how the R0 depends on T from here. Okay? So you just need to integrate this equation. So this is a simpler exercise, because now you just need to do an integral of some function. Okay? And then you find omega d minus 1 divided by 16 pi gn R0 d minus 2 minus R0 power d divided by R squared. Okay? So you get actually rather simple answer if you do that integration. So we have chosen the integration constant so that when R0 equal to 0, this is 0. Because R0 equal to 0, the black hole have 0 size, it essentially has no black hole. and we have chosen the free energy to be 0 for the low black hole. Okay. So this free energy again should be interpreted as a difference with the pure ADS. Okay. So for the black hole, this is the black hole free energy. Black hole free energy. Because by definition, in this way, the pure ADS you just have 0. Any questions about this? So now you see here clearly this expression. So now this is a free energy. Now this is not the Euclidean action. So they differ by a minus sign. They differ by minus sign in my convention. Okay. So now you see that they exist R0, critical R0. F black hole is greater than 0, free energy is greater than 0, for R0 is smaller than R. Okay? So you can write it as omega d minus 1. So let me just write, you can put the omega R0 to that out. Put the overall factor R0, put d minus 2 out, then this just becomes 1 minus R0 squared. Okay? So you find that the free energy is greater than 0 when R0 is greater than 1, and that's greater than the so this is greater than the value of the thermal ADS. And the black hole is smaller than 0. The free energy is smaller than 0 when R0 becomes greater than R. Okay? So the R0 is somewhere here. So R0 is somewhere here. Have to exist above somewhere here. So this is R0. This is this R0 critical equal to R. Let me just say. This is R0 critical equal to R. Somewhere here. Okay? So it's always a big black hole. And you can find out what is this critical temperature. So the critical temperature is just the beta evaluated at R0 equal to R. And you can find it out. This is 2 pi R divided by d minus 1. Okay, just using this formula, you can find out is that. Okay? So now I emphasize that this is a phase transition. And this is not only a phase transition, this is actually a first order phase transition for the following reason. So in our unit, below here, the free energy is 0 times order n squared. It's 0 times n squared. But above here, once you're above Tc, at Tc, the free energy is exactly equal to 0. Okay, so when R0C is equal to R at Tc, this free energy is exactly 0. So at Tc, a big black hole and the thermal ADS have the same free energy, so they can exist together. And above here, then the free energy of a big black hole is some negative number times times n squared. Okay, so your free energy have a huge change. So essentially the first derivative of the free energy is discontinuous. Okay, of course the phase transition. Of course the phase transition. So this is actually a first order phase transition. Yeah, so this is, let me just emphasize that. This is the first order phase transition. With the free energy equal to order n to the power 0 when t is smaller than Tc, and some non-zero number times n squared when t greater than Tc. Okay? Any questions?
When R0 equals to R, then F equals to 0. Right?
Yeah.
Then by the
No, the derivative of f should be discontinuous. No, f is continuous. No, this is the definition of the for the phase transition. The free energy is always continuous, and then the free. So the first derivative here would be proportional to n squared, and you can check. Yeah.
So the point is, okay, so just so you can understand. So the point is that it's discontinuous in the limit of large n or something. I mean.
Yeah, that's right. That's right. Exactly. Yeah. Yeah. So let me emphasize. So this is in the n go to infinity limit. Okay. So any other questions? So we see there's a rather rich story when you go to the sphere. And actually, there's a phase transition. And the phase transition roughly at the black hole side is the ADS radius. Okay? Exactly the black hole side is the ADS radius. And this is more or less what you expected because because that's where the physics become non-trivial. Because when the horizon is much, much smaller than the black hole size, then the curvature radius, as I said, just should reduce to the flat space black hole and etc. Yeah, because the curvature radius is only scale here. Yeah. So now let me make another remark. Now I erase this. I think it's okay. Yeah. So you should actually check yourself. So below Tc, the f prime is always 0. When you take the derivative, it's always 0 in order n squared. Yeah. Let me again write this as 0 times n squared. Okay. So you should check that the first derivative of f is discontinuous. Okay.
So f itself is not discontinuous.
Now f is not.
Okay.
Because the f is 0 at precisely at t equal to Tc. So f is equal to 0.
Okay.
Yeah. So the reason this the first derivative is discontinuous is very clear because below Tc, this is 0. So the first derivative is 0 times n squared. And above Tc, the derivative is the derivative of the free energy of the black hole at r equal to r0. And clearly the derivative is non-zero. Okay, at r equal to r0, the derivative is non-zero. Okay, and so you see they're discontinuous. Okay. So since physics only depends on the dimension is number r times t, okay? So large R, small t, large R at fixed t essentially is the same as the, say, large T fixed R, because only depend on the ratio of them, okay? It depends on the product of them. So you can either think you fix the temperature, you increase the size of the sphere, or you fix the size of the sphere, you increase the temperature. The effect the same is to increase this guy, okay? And this is essentially the limit going to the flat space. It's going to the R to the D. If you take R go to infinity, you go to a series on RD minus 1. So we see that the series on the RD minus 1 is mapped to the high temperature limits of the series on the sphere. Okay? So essentially just corresponding to the 1 point for the series on the sphere and just infinite temperature limit of the series on the sphere. So that's why, as we said before, because there's no scale here, the all temperature from here is essentially the same in the flat space. Okay? And in particular, this is described by a big black hole. Okay? And this is exactly what we see before, because when the black hole become very big, then you can approximate it to a plane, because locally it's just like a plane anymore. The spherical horizon just like a plane. And then you go to the black brane. You go to a black hole with the flat horizon. Okay?
Why the physics only dependent on R times T?
Yeah. Because this is a CFT. And this is only dimensionless number. You can only depend on them through this dimensionless number. Yeah, there's no other scale. Good. Other questions? Yes?
So on the side of the CFT, what are the different phases? I didn't.
Sorry?
What are the different phases on the CFT side?
That's what we are going to explain. Okay? So now we have described the black hole story, or now we have described the gravity story. Just by looking at the gravity side, we saw there are 3 possible phases. At low temperature, you get this thermal ADS phase. At the high temperature, you get this big black hole phase, and then there's a phase transition between them. And then also you have unstable or small black hole phase, which never appears as a stable phase at any temperature. Okay? So now let's try to see whether we can understand this from the field theory side. What does this mean from the field theory side? Why somehow, if I put, for example, put the integral super Yang-Mills theory on a sphere, do I expect such a kind of phase transition? Does this make sense? Okay. Oh, by the way, I should say this is this is called the Hawking-Page transition. So this is called the Hawking-Page transition. So remarkably, this was discovered in 1980, I think 81 or 82. Almost 20 years before this ADS-CFT conjecture. But they already figured out that there's a phase transition. They were looking at the black holes in ADS. They say, oh, there are 2 black holes. But there's also some ADS. And then somehow there's some kind of phase transition between them. But of course, they don't know the field theory. They don't know this should correspond to some kind of field theory system. Okay? Yeah, but they figured out this gravity story essentially in 1981. Okay, now let's explain what should be the field theory interpretation of this. the field theory explanation of this. Critical reason for Hawking-Page transition. Okay. So now I will consider a toy example. So we won't consider super Yang-Mills theory on the sphere. That's a little bit too complicated. But I'm going to consider a toy example. And you will see from this toy example, the physics behind this is very simple. And actually also to an incompatible Yang-Mills theory. Okay? So let's consider you have n square harmonic oscillator, free harmonic oscillator. Okay? So let's just imagine you can take them to be different frequencies. Let's just, even for simplicity, all of the same frequency. Say omega, some omega which I just take to be 1, doesn't matter. Okay? So just consider n square free harmonic oscillator. So I claim when n goes to infinity limit, this system have the same have exactly the same phase transition described there. Okay? So now I will explain. So first, let's look just this is a system we know how to solve exactly. So let's look at the spectrum. So this is total spectrum, the total energy spectrum of these n square harmonic oscillators. Okay, so let's call the 0 the ground state. So let me normalize the energy so that the ground state have energy 0. Okay. And then you can excite one harmonic oscillator, and then you have state of 1. Okay. Yeah, actually, yeah, I have state of 1. And you can have 2 harmonic oscillator, etc. Okay. And then you can have many harmonic oscillators, say of all, then you can have almost every harmonic oscillator excited, and then you have energy of order n square, etc. Okay. So now you have to imagine a slight non-trivial condition. Now you have to imagine a slightly non-trivial condition, which this is the only thing which beyond the harmonic oscillator. Yeah, actually, just realized this. I slightly oversimplified the story a little bit. Yeah. Yeah. Let me say this way. Yeah. Yeah. Let's consider 2n harmonic oscillator. So let me arrange it into 2 matrices, A and B. Okay. And they're all free. Doesn't matter. For this purpose, it doesn't matter how many harmonic oscillators. Just imagine I have arranged them into 2 matrices. Okay? So I have 2n square harmonic oscillator. And then I can excite them. But now I have a condition. So I have a condition which is analog to the condition of the gauge invariance. Is that I want all the states to be the trace singlet created by A and B. Okay? So you can have A, B, etc. So A have n square creation annihilation operator, and B have n square annihilation creation annihilation operator. And then you can act them on then you can act them to form the spectrum like this. Okay? But there's but also I need to add a gauge invariance condition. is that the states you acted by A and B have to be SUN singlet. Okay, and the SUN is the conjugate. Just imagine A and B transform under some SUN joint representation, and they have to be the SUN singlet. So equivalent statement is say that the trace A and B, all the state have to be created by operators inside the trace. Okay, single trace or multiple trace, etc. Okay, so is this clear?
So one thing. So A and B are operators, or they are?
They operate the harmonic oscillators.
Oh, I see.
Yeah. Imagine you have two matrices, and two harmonic oscillators. They form two matrices, and each of them have n-square harmonic oscillator. Okay, and if I just say they are free, then you don't even have to think about the matrix structure.
So the only thing I'm confused about the matrices.
Yeah.
So are the matrices acting on some vector? So in other words.
Oh yeah. Let me be a little bit more explicit. Be a little bit more explicit. Think about the following system. The Lagrangian 1/2 trace A dot square trace 1/2 trace B dot square minus 1/2 trace A square 1/2 trace B square. Okay? So this is the free harmonic oscillators. So these are 2n square free harmonic oscillators with frequency 1. Okay? So if I don't impose this singlet condition, this is just a purely free harmonic oscillator. Yep. Pure free harmonic oscillator. But now I require all the states, so this SUN transformation, yeah, you can act them. But now I impose a condition that they should be SUN singlets. Okay. So they can create it by A and B, etc. And but they should be a SUN singlet. Good. So now, one thing you can convince yourself is that because of the trace condition, so if you think about the state of energy 1 or 2, etc., so as far as the energy is order n to the power 0, so as far as the energy does not scale with n, then you can check yourself the density of state. The way you can the degeneracy of those states will always be of order n to the power 0. Okay, so this is a fact. You can convince yourself. And when you go to the energy of order n square, then you can check that the density of state become exponential of order n square. So the reason for this is very simple. So the reason for this is very simple heuristically. So the reason for this is very simple. Because if you have a state of order 1 which does not scale with n, means there's only order 1 states, order 1 oscillators are excited. Okay? Order 1 oscillators are excited. And then, of course, the density of state will be independent of n. And if you have energy of order n squared, because each oscillator have a frequency 1, and then if you have energy n squared, and then that means order n squared oscillators are excited. And then you have order n. If you have order n squared oscillator excited, then how many ways you can choose them to construct the state of energy order n squared, and that's exponential of order n squared. Okay? So imagine each state, you can have n possible oscillator to act, say, for each of them for twice. Okay? Then you have 2 to the order n square possibilities of doing that. Yeah, so that's where this expansion and order n square come out. Okay, so this is a fact. You should try to convince yourself if it's not obvious to you now. So the reason I add this singlet condition is for here. If I don't add a singlet condition, then there's some kind of n dependence here which I don't want. There can be log n dependence. So this makes the story a little bit cleaner. Okay. Oh. So now, I'm running out of time, unfortunately. So now let's consider the free energy, which roughly you can consider as integrate of all possible states with this weight factor and times the density of states. Okay? In this case, because the free energy sum of all states minus beta h, and the sum translates into the integral with the density of states, and then that translates into that. So naively, we always consider, so our beta is always does not scale with n. Okay, just order 1 is always order 1. So if you look at here naively, only state of energy of order does not scale n will contribute significantly because of this suppression. Okay? Because of this thermal suppression, so if you have energy of state of order n square, then this is a huge suppression. Okay, then they should not contribute. Then they should not make a visible expression, a contribution to your free energy. Except when those states have a huge density of states. Okay, so except when those states have a huge density of states. So here we see those states have actually order n squared density of states. So that means in here, in that integral, you have beta times order n squared, something of order n squared, and then times something positive of order n squared. When you consider contribution of the state of energy of an order n squared. So when this factor dominates over this factor, then the entropy will overwhelm the thermal suppression, and then such state will dominate. Such state will dominate. And that precisely happens when beta becomes small enough, because when beta becomes small enough, when you go to high temperature, then the beta decrease. So eventually this will overwhelm this one because the beta will decrease. And that's precisely the Hawking Page transition we see. So at low beta, at big beta or small temperature, this one dominates. And then Z would be of order n to the power 0, because only state of energy order 0 will contribute. But beta, when beta is sufficiently small, then the log dE minus beta E can become greater than 0. Okay? And then the order n squared states will dominate. And then you find the partition function will be exponential of order n squared. Okay? And that's precisely what we see in the Hawking-Page transition. So I emphasize the physics here have nothing to do with the details of the system, only related to the large N and to the density of states. So if you have interactions, if you have more complicated system, it doesn't matter. It doesn't matter. As far as you're in the large N limit, this phenomenon will happen. This phenomenon will happen. Okay? And so this is the essence of the Hawking-Page transition. So we'll stop here.